Electric potential energy. Objective: to derive the mathematical expression for electric potential energy for a system of point charges. Consider a fixed point charge Q1 at O. If another point charge Q2 at A, that is at a distance r1 from O, is moved to point B, that is at a distance r2 from O, calculate the work done by the electric force along the path from A to B. When Q2 is at point C, that is at a distance r, it experiences an electric force K Q1 Q2 by r square. Let the charge move from C through an infinitesimally small distance dr, during which the electric force can be assumed to be constant. As both displacement of the charge and force on the charge are in the same direction, work done by the electric force on Q2 dW is equal to K Q1 Q2 by r square into dr. The total work done from A to B is equal to integral of K Q1 Q2 by r square dr from r1 to r2. Taking the constant terms out of the integral, on integrating and substituting the limits, total work done is equal to K Q1 Q2 into 1 by r1 minus 1 by r2. Suppose the charge is taken back to point A from point B. We can get the work done simply by interchanging r1 with r2. You can observe that work done by the electric force in a roundabout motion is zero. Hence, potential energy for electric force can be defined as change in potential energy is negative of the work done. So, change in electric potential energy, if Q2 is taken from distance r1 to distance r2, is equal to K Q1 Q2 into 1 by r2 minus 1 by r1. Generally, potential energy of the two-charge system is considered to be zero when the charges have infinite separation. Hence, U of infinity is zero. If the charge is brought from infinity to r, the change in potential energy, U of r minus U of infinity, is equal to K Q1 Q2 into 1 by r minus 1 by infinity, which is K Q1 Q2 by r. Substituting U of infinity with 0, potential energy when the separation between charges is given as K Q1 Q2 by r. This expression for electric potential energy is derived by assuming that one of the charges is fixed and the other is displaced. However, potential energy depends only on the separation between charges. It does not depend on how they are oriented in space. If more than two charges are present, potential energy is associated with each pair of charges. Total potential energy of the system is equal to sum of potential energies of all the pairs. For example, potential energy of a system of three charges as shown is equal to potential energy of first and second charge pairs K Q1 Q2 by R1 2 plus potential energy of second and third charge pairs K Q2 Q3 by R2 3 plus potential energy of the third and first charge pairs K Q3 Q1 by R3 1. Let us look at an example. Three positive charges, each plus Q and equal to plus 10 microcoulombs, are fixed at each vertex of an equilateral triangle of side A equal to root 3 meters. A particle of mass m equal to 6 grams has a charge minus q equal to minus 10 microcoulombs. It is placed at a fairway point on one of the altitudes of the triangle. The particle is given a gentle push towards the centroid of the triangle. Let us calculate speed of the particle when it reaches the centroid of the triangle by applying the law of conservation of energy. Consider the four charges as one system. Compare the potential energy of the initial configuration to that of the final configuration. Configuration of three positive charges is the same in both the initial and the final configurations. The change in potential energy of the system is therefore the result of change in potential energy associated with the negative charge. Negative charge is initially at infinite distance. Hence, potential energy of the each positive-negative charge pair is zero. When negative charge is at the centroid, potential energy of the negative-positive charge pairs is equal to kq minus q by a by root 3 plus k q minus q by a by root 3 plus k q minus q by a by root 3, which is equal to minus 3 root 3 kq square by a. Change in potential energy of the system is minus 3 root 3 kq square by a. Kinetic energy of the system initially is 0. Kinetic energy of the final configuration is half mv square. So, change in kinetic energy is half mv square. Since there are no external forces acting on the system, according to the law of conservation of mechanical energy, the change in potential energy plus change in kinetic energy is 0. V is equal to square root of 6 root 3k q square by ma. On substituting the values, we get the speed as 30 meters per second. Summary. Potential energy when the separation between the charges q1 and q2 is r is k q1 q2 by r.